Hello, my friends. Welcome back. Now, our fourth lesson will be about linear regression, which is a very popular analysis in data and econometrics that helps us understand or to predict the value of a certain variable using other variables. And let's move on. What is linear regression? Is the statistical method used to model the relationship between a dependent variable and one or more independent variables by fitting a linear equation, which is, if you take a look, this black line here minimizes the difference between each point and the line itself, and it's the line that we use to predict the values of future observations or try to predict how the variable is going to behave. And it's got the typical equation that I showed you, the dependent variable here, the coefficient, this beta is where the line crosses this axis here, the y-axis, should be this, something like this. And then you have the coefficient for the independent variable and the error that should be a white noise. So let's suppose that I want to predict the price of a car, of a new car, by using as an independent variable the mileage consumption. Of course, that's not the only variable, but it's just for us to show how this logic works. So imagine that we want to understand the relationship between a car's price and its fuel efficiency, miles per gallon, or MPG. The hypothesis is that a car price is related to its mileage. And the equation is quite simple. The car price depends on a certain constant variable here, and this coefficient applied to the miles per gallon consumption that this car makes. Let's suppose that we run this, and that we have a database, and then we run the linear regression model in some of the softwares that we use, any of the softwares that we're using in this course. And then you have this table of coefficients here, right? So let's understand this table. The first thing you need to look is the p-value to see if this variable is relevant. If the p-value is smaller, p-value is smaller than 0.05, and that's considering a 95 percentage confidence interval. If this value is smaller, then this coefficient is significant. It's a useful coefficient. And the same thing for the constant, and because it's also below 0.05. And the r squared, which is also very important, is very small here. This model here, which has only one variable, only explains 10% of the price of the car. Okay, but still, what is the idea here? Of course, this example is not a real example. It's just for us to understand the logic. So imagine that the car price starts at this value here, which is the constant, because if this value is zero in the equation, right? You have the coefficient times zero is zero. So the car price starts here. And because it's got a negative effect, let's consider this is the mileage per gallon, right? Every time the mileage per gallon increases, the value of the car decreases. So if the car spends less gasoline, less fuel, the price also goes down. This is what this model says. Of course, I don't think this is connected to reality, but it's just for you to understand the logic of the model. Here, there's the interpretation of the coefficients. So a negative coefficient, or that beta 1 on that equation, suggests that more fuel efficient cars tend to be cheaper. If this value was positive, then the line would go up, and we would have a different result from that. The constant is relevant because of the p-value is very small. Of course, this doesn't make sense in reality. You don't have a car that spends 0 miles per gallon, but you understand the logic that the car starts at a certain price, right? There's cars, the cheapest car starts with a certain price, and you take that into account by this beta 0 here. And the p-value was very small, which makes us consider that the coefficients are true. And well, just for you to see how, if this model was correct, this would be the coefficients. This coefficient goes here, this coefficient is this one, and that would be the equation for us to determine the price of the car. And what if I want to put more than one variable, right? Because in real life, this variable doesn't make sense. What if I want to choose try to define the price of the car by using other variables combined? Can we do this? Yes, of course we can. We just use the same rationale for each variable and then combine them into one equation with different coefficients, one coefficient for each independent variable. So going on with this example, let me consider 3 independent variables here. So fuel efficiency keeps existing. The car weight, let's suppose that the car weight makes a difference in the price. And another dummy variable, introduce this for you to understand what the dummy variable is. So if the car is produced locally or if it's an imported car. And the equation should be this one. So the price of the car, it has a constant here, and then one coefficient for the miles per gallon, one coefficient for the weight of the car, and one coefficient for this dummy variable if the car is imported or domestic. And let's suppose that after we run the analysis on our software, we find this table here with these coefficients. So first thing we look, p-value, this is way, way over 0.05, right? Way over. So what do you understand? That this variable, we can't use this variable because it's not a good prediction. Weight, it's got a small p-value, and foreign also a small p-value, and the constant also way above 0.05, so we don't use this. And r squared is 48, so which means that our model explains 48% of the total price of the car. So we just use two variables, two coefficients here with these two variables, which is the weight of the car and if it's foreign or if it's imported or domestically produced. And we're going to have an equation that same style, right? The price of the car. In the end, it's going to be this. The constant is not relevant, so we don't use it. And then we have this beta 1.74 for the weight of the car plus 3,673 times this variable, which can be 0 or 1. And then you have to define in the model if 1 is domestic or 1 is imported. So interpreting these results, we have the coefficient miles per gallon, or beta 1, that has a very large p-value, way more than 0.05. We understand that the car costs $3,673 more if it's a domestic car, highly significant. The weight is also significant, and the R-square shows that 48.8% of our the variation of the price is explained by the variables that we use in our model. And that's the rationale behind linear regression with one variable or multiple variables. I also run this analysis on softwares on our next classes, so you can understand how this works in practice, and you can use your data to build your own models on linear regression. Okay, thank you. See you in our next classes.